Hello and welcome to this keynote from Java 21 to 25, where I'm going to talk to you about what happened in the past few versions. 21 was released just about a year ago, and what we can tell about the upcoming features as 25 is to be released in about a year. Maybe some of you remember that I did a similar presentation 2 years ago with a very similar agenda. But don't worry, I checked it very precisely to be sure not to repeat what you already saw. My name is Jose. I am a Java developer advocate at the Java Platform Group here at Oracle. And here are some links with the content I publish on the web. If you're interested in more Java content, you can check my GitHub account where you can find a lot of demos on the elements you are going to see today. And here are some more links with the content we publish at the Java Platform Group. There are videos with the Inside Java newscast held by my friend Nikolai with the help of Billy and Anna, the SIP of Java by my friend Billy, and the Inside Java podcast in case you don't like videos, which is fine. And of course, the dev.java website with all the documentation you need on the Java language. Just before we start, I would like to talk a little about the OpenJDK, which is in fact the place where you need to go if you're looking for information about what is currently being developed in Java. This is the place where it all happens, and all the projects we are going to talk about have a page and sometimes an early access distribution available there. As it is the place where everything is happening, this should be your number one source of information and the most reliable one. If you check the jdk.java.net page, you will see several JDK builds, including builds for experimental branches. So if you want to try the new features developed as part of the Valhalla project or the Loom project, for instance, you can do so from this page. Why is this talk called From Java 21 to 25 and not 23, for instance, that was just released a few days ago? Well, as you know, the JDK 21 is the last so-called LTS release of the Java platform. And because people and companies use these LTS releases, odds are that the version you are currently working with is an LTS version. Along with the release of the JDK 17, the LTS cadence went from 1 every 3 years to 1 every 2 years, meaning that the last LTS is 21 and the next one is precisely 25. That being said, LTS may not mean what you think. If you check the OpenJDK website and the JDK distributions you can download from this website, you will see no trace of these so-called LTS version. From the OpenJDK point of view, there is no such thing as LTS and non-LTS releases. Every version is production ready. The version 20 has the same level of quality as 21, 22, 23, and is certainly not some kind of beta version of the so-called 21 LTS. LTS is a decision from the JDK vendors to offer some support for a longer time. These versions can sometimes be freely downloadable and usable under some license that you need to check. It is, for instance, the case of the Oracle JDK 21 that is freely available until 1 year after the release of the Oracle JDK 25. So you have enough time to organize the migrations of your projects. You may be thinking that having a version every 6 months or an LTS version every 2 years slows down the release cadence of the features added to the JDK. Well, here is a chart that shows you the contrary. In fact, the number of features released per year is increasing. So making the cadence faster brings you more features and faster. I would like to cover 4 OpenJDK projects in this presentation, namely Ember, Loom, Valhalla, and Panama. But before deep diving into each one of them, I would like to spend a few minutes to give you an overview of all of them. The first idea of the AMPER project was to add a feature called pattern matching to the Java language. This is a feature that comes from functional programming, which is nothing but new. But then it became much broader than that. Sure, you can use pattern matching in your code, and this is great, but it is actually an element of a larger picture that you will see. Then there is the Loom project, which is about concurrent programming. There are several things that Loom wants to fix in a concurrent programming model in Java, including getting rid of the callback-based asynchronous code, sometimes called reactive code, that leads to applications that are complex to write, hard to read, hard to test, and impossible to debug or profile. The Loom programming model is based on imperative programming, much simpler, and the model of virtual threads makes it so that the performance are the same as reactive programming. Valhalla is about redesigning the way objects are laid out in memory to get rid of pointer chasing, if possible, and bring better performance without having to sacrifice the modelization of your domain objects. Valhalla is just about that, not having to choose between performance and readability. Again, cleaner code, better performance. And at last, Panama is about rethinking the way you can access native code from a Java application. First, Panama brings the vector API that gives you the access to the SIMD kernel of your CPU. And second, it brings you a new API to execute your C code, for instance, and the handling of the off-heap memory, the one that is not managed by your garbage collector. So this is what this presentation is about, showing you how Java is evolving to bring better performance, new ways of designing your application and your object model to help you write cleaner code that will be less expensive to maintain in the future. Let us start with the project Valhalla. And before we start, let me remind you that you can download an early access version of the Valhalla project on the jdk.java.net webpage that was released at the end of July to try all what you are going to see in this part. I guess, or hope, that you all heard about this design pattern book, and maybe you read it. And if you check the introduction of this book, on page 20, there is this well-known principle, favor object composition over class inheritance. And the fact is, nobody follows this principle. If we did, we would write wrapper classes everywhere to give some business meaning to int, long, double, strings of characters, or plain dates. And it would work great from a modeling perspective, because you cannot extend int or string or date in Java. As you can see on this example, having an array of int called populations is much faster if what you need to do is to sum all your populations. If you write this for loop as a stream, odds are that some tech lead will come to you and tell you that you can't write this code. Why? Because it is too slow. Which is unfortunate because it's much easier to read and easier to maintain, so also cheaper to maintain in the long run. If you push this idea one step further, creating a population record and using it in a for loop or in a stream would even be more readable and less error-prone. But the problem is that what you have is, on the one hand, an array of values that are int values, and on the other hand, an array of references that you need to read to get the value you want to work with. And whatever you do, this array of references will never be as fast as an array of ints. And the situation could be even worse, because this is a very simple object. Suppose that you have a collection of cities with a population in it, and you want to regroup these cities by state and sum their population. What you are basically building is a very simple thing. It is called an histogram. And an histogram is modeled by a map of state and population that you will model with a string, that is the name of the state, and an integer, that is the corresponding population. And then you need to add some comments in your code to explain that this string is actually the name of the state, and that this integer is actually the population. Which is a pity because you could model all this with 3 records: state, city, and population, and create a map with a meaningful model. But the layout of this map in memory would be a disaster. What you have is a hash map that is an array of references to entry objects. The value of your entry is a population object, and the key is a reference to a state object that contains another reference to a string and yet another reference to the array contained in the string. Nice model indeed, but it comes with a cost that you don't want to pay. The first goal of Valhalla is to make abstraction almost free. The motto of the Valhalla project is "codes like a class, works like an int." So how is it going to work? First, it creates the notion of value class. That is a class that is bound to carry only a value, like the population record of this example. To efficiently lay out this kind of class in memory, you need to give up on some elements. And in that case, what you need to give up is the identity of this class. So a value class has to be final. All its instance fields are final, which is okay because it's already the case for records, but that's not all. The instances of such classes do not have an address, so you cannot synchronize on them. And when you compare these instances with equal, what you are comparing are the fields of your instances. You cannot compare the address anymore because precisely there is no more address. That being said, records can be made value records, that is, value classes. So declaring the population record or the city record in that way, with this syntax, in the JDK Valhalla preview that we talked about, is actually possible. With such a declaration, you are one step closer to the memory layout you want. Instead of having an array of references, you could have an array of inlined ints. But you're not quite there yet, and you need something more. Let us take a step back and ask the question, what is a primitive type? Well, it does not have an address. Equal compares the value, and it is non-modifiable. Modifying a value just doesn't make sense. So far, it looks like a value type. But there is more. It also has a default value and cannot be null. Think of ints, for instance. Which raises a question about arrays. Suppose that this population record can be seen as a primitive type. Since a primitive type cannot be null, declaring such an array should not contain null values, as it is the case for arrays of references. But it should contain the default value of population, which could be a population of 0, for instance. But the fact is, you can wrap this array in a list with arrays.asList. And on list, you can set an element of this array to null. Of course, this code is legal at compile time, but at runtime it would fail since the wrapped array does not accept null values. So defining such primitive-like types requires several things. First, you need to be able to define the default value for your value class. And second, you need something in the type system to tell the compiler that this type does not accept null values. And this is new in Java. So far, to define that a class or record has a default value is declared with the annotation at implicitly constructible. But the goal is to make it a language feature with a bang character. If you need to declare that a field in a class cannot be null, then you need to use the @null_restricted annotation, but the goal is to make this bang character usable here also. With all this, you can now tell the compiler that your array or your field cannot contain null value. And the same for class parameters. You can declare a list that cannot contain null value. So now the compiler can see that you are trying to do something wrong if you try to set this value to null. This syntax is not yet supported by the early access version of Valhalla, but you can still create arrays of non-nullable values using this API. So now, instead of having an array of cities that is laid out in that way in your memory, you can inline everything as long as you declare an array of non-nullable cities built on a non-nullable population field. Remember that both the city class and the population class should be implicitly constructible. Many well-known classes of the JDK will become such classes. All the wrapper types, integer, long, double, and the like, as well as optional, local date, and others. All this is available in the early access build of the Valhalla project based on the JDK 23. So that's it for Valhalla. Let us now talk about Panama. There are three elements in Panama that I would like to talk to you about. First part of Panama is the vector API, which gives you a direct access to the SIMD assembly instructions you have on your CPU. This API is still available as an incubator feature. That's the 8th incubator in the JDK 23 and will remain in the incubator state until Valhalla is delivered. The reason is that the types of the vector API are bound to become value types, so no Valhalla, no vector API in its final state. Then we have the foreign function and memory API, FFM for short, that was made final in the JDK 22. And this memory API is what I would like to focus on. The memory API is about accessing the off-heap memory of the JVM, that is the memory that is not managed by your garbage collector. How can you access this memory as of now? Well, you have several solutions. The first one is to use the byte buffer API designed with Java 4 in 2002. This API has several issues that the memory API wants to fix. The second one is to use JNI, which is not ideal. And the third one is to use unsafe, which is, well, unsafe precisely. The byte buffer is an API that has been working for 20 years, but it still has some issue. And the first one is that it manages pieces of memory that are indexed with an int. So you are limited to a number of elements in a byte buffer, which was not really a limit on the 32 bits operating system, and that was the case in 2002, but it is a limit nowadays. The other major issue of the byte buffer API is the way they are closed. You cannot close a byte buffer yourself. The closing of a byte buffer is actually managed by the JVM and the garbage collector. And this is a very serious issue, especially when a byte buffer is used to map a file to your memory, because you can close your file but not your byte buffer. So it is still possible to try to read or write some data in your byte buffer while your file is already closed. The memory API brings you a completely new model that is still compatible with byte buffers if you still need to use them. It relies on three main types. The first one is the arena. This is the top-level type. You can see an arena as a collection of segments of memory that share some common behavior. The second one is the memory segment that models a contiguous zone of your memory. You can get a memory segment from an arena, and when you close your arena, all its memory segments are made unavailable. And the third one is the memory layout that models the data contained in a memory segment. Let me take you through a simple example to see all this in action. Suppose that you have the following C struct written in a point.h library. pretty basic. It's just a point with two coordinates that are integers. And suppose that you need to read or write instances of this struct in the memory of your application. The first step you can follow is to use a tool called gextract, which is not yet available as part of the JDK 23, but you can download on the jdk.java.net page for the JDK 22. You can run gextract in that way, and it will generate some classes for you. It generates one class for each library that you have, plus one class for each struct defined in this library. So here it generates two classes. Note that the class for this library is called point_h, all in lowercase, and point also in lowercase. Note that there is no function defined in this library, but of course you can if you need, and gextract will do something with them. So let us first write a point in memory. For that you need an arena that you can create with the of_confined factory method in a try with resources statement. And once you are done, this arena will be closed and all the memory segments you created from it will be made unavailable. So that's one byte buffers problem fixed. You can then use this arena to create memory segments. And what it does is that it gives you a segment of memory that can contain exactly one point in this example. Now, you can write something in this segment by passing it to one of the factory methods of the point class. gextract created one for each of the fields of your struct, so here x and y. Calling x like that sets the value of the x field to the value you pass as an argument. Reading that value calls an overload of the x method that only takes the segment as an argument. As you can see, reading and writing is made very easy, very clean and simple pattern, thanks to the code that gextract generated for you. You can also read and write arrays of points. These patterns use the patterns you just saw. The first point is still to create an arena using the same pattern, and then use the allocate array that gextract creates on your point class. This gives you a memory segment that can hold the number of elements you passed as an argument. And this argument is a longer. Then, to write or read this segment, you need to get another segment that is just a subsegment of the array segment with the method asSlice that takes the index of the element you want to access. This subsegment is just a view on the array segment, so there is barely any overhead in creating it. And then what you have is the exact same segment as in the previous example. So you can use it in the same way to read or write values at this index in your array. And keep in mind that this index is a longer. You can also adapt this pattern in a loop, here on 4 elements of your array, and then you need to slice it and read its content. As you can see, these patterns are pretty simple thanks to the code generated by gextract. And the next step is to be able to map a file to a memory segment, just as you used to do with a byte buffer. So now you also need a file and an arena, just as previously. You can then create a memory segment from this file channel by passing the arena object. So now you are back to the previous problem. You can use the exact same pattern as the one we just saw. But instead of using a for loop, I would like to show you another pattern based on the use of the stream API. You can call the elements method of memory segment and pass a memory layout to it. Memory layout is also a class given you by this memory API. Here you can use the layout method that gextract created for you on a point class, but you could also create your own layout using the memory API. The stream you get is a stream of memory segments, like the sliced memory segment you just saw in a for loop. So what you can do is map this memory segment to the x coordinate, for instance, that you can also write as a nice method reference, by the way, and then compute average, for instance, on that stream and put the result in a variable. And you can see that the pattern it gives you is very simple, very clean, and also very fast. And that's the quick overview I wanted to show on the memory API, part of the PAUMARD project, which made it as a final feature of the JDK 22. Let us now move on to the Ember project. As I said, Ember started with a few features that are useful to the language, and by the way, used in many places in the JDK source code itself, and soon unveiled a much broader and much more ambitious goal. It is all about implementing old ideas about data-oriented programming and the expression problem. Now, the expression problem is nothing but new. Here are some references from the 70s. And it is about extending an object model. They used to call that data abstractions on the papers from that time. Phil Wadler from the University of Edinburgh studied this problem and discovered the following. Suppose that you are given an object model in the form of a separate module that you are not allowed to modify. This is a very classic situation that you probably know in your applications. Well, in the context of object-oriented programming, you can extend the classes of this model, that is, create subtypes of the types you get, but you cannot add operation, that is, methods, on the existing types. There is no way you can add behavior on the existing types of the object model you get. In the context of data-oriented programming, all the types you get are sealed and you cannot extend them. So you cannot create new types. But you can add new operations on these types. And what Phil Wadler showed is that you cannot have both. Either you can add new types by extension, or you can add new behavior, but not both. Now, we've all been working with object-oriented programming for decades, and we all know how it works. So the question is, what can data-oriented programming give you that object-oriented programming cannot? And for that, let me take you through a small example. Suppose that you are working on an application that can book flights, and you are working on the business module of this application. Each one of them implements a single business process, and you can get an object model that you can work with. Within this object model, there is this big flight class with 50 fields and 80 methods, probably an entity mapped to your database that you need to work with. And you hate that because this object is way too big for your need. And then there is this booking process and this payment process to buy seats in these flights. And here is the first weird thing. You pass a flight object to your booking process so that it can call one of the methods of the fly object, because this is where the behavior is. Who thought that this is a good idea to work like that? Let me show you how dependencies are working between the modules of your application. Obviously, the two business modules both depend on the object model at runtime, and there is no way you can avoid that. But they also depend on this module at compile time, which is actually very annoying. First, it is in contradiction with the interface segregation principle. That's the I principle of the solid principle, because your flight booking business module depends on the many methods of this flight class that it does not need. And this is annoying because every time there is a modification in this flight class, you will need to recompile and rebuild your flight booking module, even if this modification is of no interest to you. But it is also in contradiction of the D principle, which is the dependency inversion principle, that states that your object model should depend on your business module and not the opposite. High-level business rules should not depend on low-level technical implementation details. So when it comes to the organization of your modules, this application is already in a bad situation. And it is in fact worse than what you think. Suppose that now you have a new business requirement. Your application should support multi-leg flights. How can you handle that? Your reflex will probably be to extend your flight class because a multi-leg flight is a flight. And this is in contradiction with the third principle of the solid principle, which is the L principle, the Liskov principle. The Liskov principle tells you that if a class B behaves as a class A, then B extends A. It actually defines what inheritance is. Obviously, a multi-leg flight does not behave as a flight. So according to the Liskov principle, it cannot extend flight. If you still do this extension, then problems will arise. You will end up with random instance of or methods that throw unsupported operation exception in your business module, and it will be a mess. We've all been there, and there are way too many applications out there that have followed this path. This kind of decision has a name. It is called technical debt. What kind of solution would data-oriented programming give you? Instead of extending flight, data-oriented programming tells you to make it an interface with no method in it, so no behavior. And this interface should only have two implementations: simple flight, which is the original flight class, and multi-leg flight. And remember, you cannot extend types in data-oriented programming, so this flight interface is sealed, and the two implementations can be made records that do not carry any behavior, only state, and that are final because a record is a final class. And of course, your business modules still declare flight as a parameter, so the refactoring on this side is minimal. Where are you going to implement the processes themselves? Well, the code will be there where it should be, in the business modules themselves. So when you get a flight object, you need to check what is its real type and implement the proper behavior there. Reason why you have a switch on types. You actually need this feature for data-oriented programming to work. And if you have record deconstruction, which is the case, then your code becomes even simpler. It also becomes more robust, because if you change your model, that is, if you add or remove types that implement your sealed interface, or if you add or remove components in a record, then the switch that you wrote will not compile anymore. You may be thinking, yes, but records are non-modifiable, so how can I handle modifiable fields? For instance, how can you handle that the price of a flight varies over time? Well, all this tells you that the price is not part of the state of a flight, because in this model, a flight is a non-modifiable element. So it means that the price is actually the result of querying some kind of pricing service that will give you the price at the moment you make this query. And if you think about it, this actually makes perfect sense from a business perspective. How is this price calculated? Well, that's a business rule, but now this price may fluctuate. Second question, how can you handle the fact that your object model is made of Hibernate entities? These entities are modifiable, so they cannot be records. Well, to handle that, you need to consider your seal types as an intermediate model between your Hibernate model and your business processes. Your business processes are at the center of your application, and they define the seal types and records they need. And now they actually follow the interface segregation principle. These types are part of your business modules. Then it is the role of your Hibernate module to adapt the entities to the seal types each module defines. Your Hibernate module becomes a client of your business modules, so at compile time, it depends on your business module. all its complexity is now hidden from your business code, which will make your life much easier. And since at runtime your business modules still depend on your Hibernate modules, then you are now also following the dependency inversion principle. Adding new types consists in updating the permit clause of your sealed interface, adding or removing new records. So you will need to fix all the switches that are not compiling anymore in your code. So in fact, it's a minimal refactoring and very clean and very safe thanks to the work of the compiler. All you need to do is focus on the complexity of your business rules, not on the technicalities of your code. Plus, as a bonus, you make it very simple to remove elements when they are not needed anymore. Every business process is cleanly separated from the others. Every sealed type and the corresponding records are defined within each business module. They are not shared. So it is actually very easy to remove them when they become obsolete from a business point of view. Suddenly, you can get rid of dead code in your application, which is much harder, if ever possible, in a classical object-oriented approach. So let us quickly wrap up all this. Records, pattern matching, for instance, of and switch, seal types, type patterns, record patterns, unnamed patterns, all this is now final in a JDK. There are still elements that are coming, primitive patterns, which is a preview feature, and more to come in the pattern matching field. Let us now talk about the project Loom, which is about fixing issues in the Java concurrent programming model. First question, why do you need concurrency? Well, because it is the way to execute several things at the same time on any CPU. And you need that to achieve high throughput in your applications. As of now, this is achieved by the callback-based reactive programming model, and this has been the solution for more than 10 years now. Why do you need reactive programming? Let me take you through the following example. Suppose that you need to build a page from links and images. The simplest code you can imagine would probably be the following. But as you also know, this code is way too inefficient to be used as is. Why? Because each request takes milliseconds, if not hundreds of milliseconds, and it is a waste of time not to launch them in parallel. Good. So starting with the JDK 5 that was in 2004, you can use the executor service pattern, which gives you this kind of code. Now, all your requests are executed in parallel, which is better. But unfortunately, this code still has issues. First, it blocks 3 threads. The first 2 are the threads from your executor service, and the third is the thread that is calling get. Blocking a thread is bad because it is an expensive resource and you should do your best to keep your threads busy. But unfortunately, that's not the only issue. There is another sneaky bug in this code. Suppose that the first call to get throws an exception. Then the thread that made this call is now broken and will not call the second get in this code. So if something goes wrong in readlink, if this task never returns, then the thread executing it will never be freed. So you spent quite some time fine-tuning your executor service and decide that 12 threads is the optimal number of threads you need. Well, guess what? Now you have 11 to handle your tasks. And after 2 more days, you only have 10. And after a week, you only have 3. You investigate because you have performance issue in your application, but can't find a reason why some threads of your executor service are not working anymore. So all you can do is reboot your application and repeat that process next week and again the next one and again and again. And there is no way you can find this bug, apart from checking your source code very carefully. Loose threads are a big issue in this pattern. And there is a third issue. This code is very hard to debug, mostly because the stack traces you have when an exception is thrown in your tasks are not helpful. And I will show you an example of that in a minute. So we have 3 issues to fix. Blocking a thread is bad, it shouldn't. Having useless stack traces is annoying, we need meaningful stack traces. And having loose threads is a pain, so we need to find a way to get rid of loose threads. Does reactive programming fix these issues? Well, let us take a look at that. Here is the way of writing the previous code with the completable future API. The fact is, this code is efficient, and you can achieve excellent throughput with this approach. And this has been the case for 10 years. But the first cost it comes with is that it's not super easy to write, probably even harder to read or unit test, and super expensive to maintain in the long run. If you need to modify this code to follow your business requirements, then you'll probably be in trouble. Note that the handling of exceptions is not made in a try-catch, but rather in a call to this whenComplete method. What about debugging this code? Suppose that something goes wrong in the readImage call and that an exception is thrown. In a classical imperative way of writing your code that you do not use, your stack trace takes you exactly where this code was called in your application. So if you put a breakpoint there, you will see the full context of this faulty call. Suppose that the same exception is thrown in the executor service pattern. Well, you will get this stack trace. It does not take you to the place where you passed this task to the executor service, where your lambda was defined, but to the place where you call the get method of the future object. In this example, it's not too bad because it's close enough to the call to submit, so that's probably okay. But in a real application, it could be kilometers away. The information of where submit was called is lost, and this is annoying. What stack trace would you have in the completable future case? Here, I just added some code in the whenComplete call to display these stack traces. So here they are. The first one does not give you any information because it's a completion exception that wraps the real exception. And here is the stack trace of the root exception that is even worse than the executor service one because it does not give you any information on who called your service and where was it called, where your lambda is. It takes you in your reactive framework, and that is useless for you to debug your problem. This makes your reactive code impossible to debug, and for the same reason, impossible to profile. Loom brings a new model of threads, which is called virtual threads. There are 3 things that you need to know about virtual threads. First, they are lightweight objects. You can create literally millions of them in your application. So trying to pull them is completely useless. Don't do that. Create them on demand and let them die when you're done with them. Second, they run on top of regular platform threads, sometimes called kernel threads. But, and that's the third point, blocking of virtual threads does not block the platform thread it is running on. Blocking a virtual thread is okay, and it's almost free. There is an overhead, but very small. So with such a tool, using a regular imperative coding model becomes okay again, because blocking a virtual thread is cheap. You can and actually should do that. The code you write is the most basic one. Now, suppose that something goes wrong in your task. Because it is classic, basic imperative programming, now you have stack traces that take you where your task was called. As you can see there, the stack trace takes you to the line 78, where your callable is declared. Now you know where you are in your application, debugging becomes much easier. And in fact, it becomes possible. You still need a programming model that allows you to run tasks in parallel. And this model is called structured concurrency and uses an object called the structured task scope. You can think of this structured task scope as some kind of executor service that could create virtual threads on demand. And because they are virtual threads, you can also create this scope object on demand instead of putting it, as it is the case for executor services. This scope object is auto-closable, so you need to use it in a try with resources statement, just like that. Old pattern from the JDK 7. Then when you submit tasks that will be executed in their own virtual thread, what you get in exchange is a subtask object, an object that looks like a future. Then you need to call join, and join is a blocking call until all your tasks are done. And then you can analyze the results by querying your subtask objects. Now, this is the basic pattern. The structured task scope class has several extensions, implementing different behaviors, with maybe more to come, since this is still a preview feature. When this object is closed, everything is cleaned up, even the structured task scope that could have been created by your tasks. So no more loose threads, one more problem that goes away. Great. What if something goes wrong? Remember this annoying read image service that keeps throwing exceptions? Well, we are in a virtual threads world. So yes, the stack trace that you get takes you where your task is created and submitted. You know exactly where this faulty lambda expression is in your codebase. Debugging is made much easier than with a reactive framework. So here are the issues fixed by virtual threads and structured concurrency. First and foremost, you are back to an imperative programming model, which is much easier to maintain because it's easy to write and easy to read. Blocking a virtual thread is okay. It does not block any platform threads. Writing blocking code is okay. It's not a bug anymore, as it is the case in the reactive world. And third, if something goes wrong, virtual threads give you stack traces that you can actually use to debug your code, which is exactly what you need. And lastly, having loose threads is not possible anymore, thanks to the structured concurrency pattern. Using virtual threads leads to the same performance as reactive programming with a much simpler programming model, with the possibility to debug your code efficiently thanks to the stack traces that you now have and the possibility to profile your application and not your framework. So let me wrap up this part on Loom. Virtual threads were made final in the JDK 21, where structured concurrency is still in a preview state as well as scoped value. There will still be a preview in 24, that's the plan for next March, mostly to get more feedback on the patterns. So if you have played with this API and have feedback or use cases that you'd like to share, connect to the mailing list of the Loom project. That will be very helpful. And with this, I think that I've covered all the elements I wanted to show you. So thank you for your attention. And if you need more information on this topic, you can check the links I added at the end of this slide deck. Thank you, and I hope to see you next time.